All right, we're back. We're on page 11 of notes 2 of Calc C. We're kind of moving along. I don't know. We're doing some Taylor polynomial stuff, looking at errors, intervals on which the true value could fall. I don't know, all the good stuff. So going to use calculator extensively on this, and also I'll be like handwriting as I go, I guess. So let's see, switching over. So cosine squared of x, I guess, is what we're really dealing with. So let's see if we can make that happen. So new document for me. Maybe new problem would have been a good choice, but 19 documents ago, I decided not to do that. So f of x is cosine of x and then squared. And then I want the Taylor polynomial. So if you do menu 4C1, I believe we'll do it. But I'm just going to type in Taylor f of x comma x. It's centered at 0. That's good. We need 3 non-zero terms. I don't know. I'll try 3 and I'll see. Nope. Let's try 4. Okay, there you go. That's 3 non-zero terms. So an interesting question is kind of like, it's cosine of x squared. Could we just do cosine series? So if I do, or polynomial, I confuse those because I should really just start with Taylor series, but it doesn't really make sense to do that. But like Taylor series just continues the trend forever. Like find the pattern and keep going forever, you get a series. These are polynomials because we're cutting them off and they just stop. So I'm gonna do Taylor cosine of x comma x. And then if I take the first 3, I need the 4th degree for that, I think, or is this. And then if I multiply these together, it's going to get, so I'm going to end up at the 8th degree. So I'm going to multiply this by itself, answer times answer. I've never actually done that before, answer times answer. I'm going to multiply it by itself and see what happens. Let's expand this. Stop obscuring what I'm going for. All right, so let me delete this. And I'm also going to delete, so I found the Taylor polynomial, 4th degree Taylor polynomial for cosine, multiplied it by itself. So that should be cosine squared. And I got this thing. And if you look at the first 3, so here's a weird thing that you may have noticed. You write your Taylor series starting at the constant and then increasing, which is the exact opposite of what you learn in algebra, where you always go highest degree to the bottom. The problem with a Taylor polynomial is that if you keep adding terms, like what are you going to just slide everything over 1 every time? No, you always add them at the end, which is why we write them like backwards. So 1 minus x squared plus x to the 4th over 3 is what we got, 1 minus x squared plus x to the 4th over 3. So it looks like we can take these polynomials and just multiply them. And that's going to be an interesting thing that we want to do. But anyway, we definitely got this. So let me write it down. So p of x is going to be 1 minus x squared plus x to the 4th over 3. All right, so evaluate your polynomial. So did I store that? I did not. Let me first get rid of this. All right, p of x is this. All right, so p of 0.5. 0.771, I guess. P of 0.5 is approximately 0.771. All right. I'm a firm believer. I didn't do it, and I'm fixing it myself right here. I feel like you should do, put in the 0. Like do 0 point. Because then there's never a question for the person who's reading it. Like, is there a decimal? Is there not a decimal? Was there supposed to be a decimal? You know, like that kind of thing. All right, to get a 4th degree polynomial, we use the 4th derivative, which means to find m, we're going to need the 5th derivative. So m is going to be, in this case, the maximum. Do I switch back and write it? I think I do, because I can't avoid that, because I don't know, I feel compelled to make sure that you are seeing this step, because this is the big step. This is the one where I see people screw up all the time. So m, we need the maximum on the interval from the center, which is 0, to what we're plugging in. So 0 to 0.5. 0 to 0.5 are really far apart. So from a calculus standpoint, the absolute value of the 5th derivative. So that's going to be, I don't actually know what that is. Let me just rewrite. Let's copy and paste. So duplicate you. That picked up a very little bit of time. Let me go back, because I don't know what the 5th derivative is. I don't have a clue actually, because it's cosine squared. Derivative f of x, comma x, fifth derivative. Okay, so negative 32 sine cosine, which you could rewrite if you do t collect on this thing as negative 16 sine of 2x, I think. Yeah, so I'm going to use, so this is the maximum of the absolute value of negative 16 sine of 2x. What are the ramifications for not knowing that? Well, I guess you would end up using 32 instead of 16. I'm going to use 16 for m. 32 is just, your interval is just going to be twice as wide because 32 is twice as big as 16. It's better to have a bigger interval when you're approximating because then you're more likely to capture the true value. So it's a valid thing to do. It's just like, because I noticed that, I went for it. Sine of 2x is a super good formula. Sine of 2x is 2 sine x cosine x. One of the most important that you can have, so that you can know, because it comes up. Sine of 2x, cosine of 2x also comes up a lot. Cosine of 2x comes up in like weird situations where you're, I don't know if weird is the right word, but it's called a power reducing formula. You can go from cosine squared down to cosine, but in doing so, you also double the argument. You go from cosine squared of x to cosine of 2x. So pluses and minuses, I don't know. All right, so the error that I'm gonna find is gonna be my value of m, which is 16, the absolute value of 0.5 minus 0, so just 0.5, to the, so we did the fifth derivative, so we need to the fifth, 5 factorial, really small. So this is gonna be pretty close. So I gotta actually write that down. So the absolute value of the error, you should also be writing this down, less than or equal to 16, the absolute value of 0.5 to the fifth over 5 factorial, which I'm just gonna store that, which I did. And then our range, right? So the range is gonna be P of 0.5 minus error to P of 0.5 plus error. So that's a tiny little range. And then we really want to know, like, is this in the middle of those? And it is. So we got it right. So let me, I'll switch back so you just don't have to watch me like talking my way through it. But you should have been writing, hopefully. I'm going fast though. I don't know. I feel like a lot of my students do these on 2x, like watch the videos on 2x speed. And I don't know how that works out for them, but that's also definitely what I would do. So P of 0.5 minus E less than or equal to F of 0.5 less than or equal to P of, because it's a lot, man. Like these videos, as much as you might hate watching them, imagine making all of them. Because that's what I've been doing for like months on end. Which, I don't know, we'll find out if I regret it. I don't think I do. But proof is like far down the road, I guess, because I don't really know like how effective anything is in the environment that I currently find myself teaching in. I hope it's effective. I mean, I'd hate to think I'm wasting my time. Like I know over time enough people will watch these to make it worth my while, but whatever. This is like my diary, doing a vlog here. Real talk, everybody. I don't know. All right, I'm gonna do one more because there's only one more on this page. So f of x is radical 7 minus x. All right, I'm gonna like start, before I do anything, let me just, so I'm gonna need to find the maximum on the interval from, all right, so it's the interval from the center, which is 3, to the value that I'm plugging in. The value I'm plugging in is kind of weird. I'm plugging in 2.77, right? So I'm doing so I want the maximum of the n plus first derivative. I don't know what that's going to be yet, so I'm not going to write that, but it's definitely from 2.77 to 3. So 2.77 to 3 of the absolute value of something, and I don't know what. So I'm going to go to the calculator now, and I hope that you were seeing all that because I was actually on my screen. I was on the calculator the whole time. I just realized. So new. I'm gonna do it. New problem. There we go. I'm not gonna hit document 20, at least not here. So f of x is kind of a gross function. Radical 7 minus x. All right, so I need the Taylor series, Taylor polynomial. Stop messing that up. F of x, comma. I firmly believe that yelling at myself will make that happen. I'm gonna say 4 and see if it works, but I need to center it at 3. So I'm asking for the 4th degree thing. I'm guessing that that's gonna have 4 non-zero terms. Nah, I think I only need 3 to get, because it's the 0 through the, let's try this. 1, 2, 3, 4. There you go, nailed it. All right, so I'm gonna hand write this in, call it P of x. So that's 2 minus the quantity x minus 3 over 4 minus the quantity x minus 3 squared over 64 minus the quantity x minus 3 cubed over 512. So this is my polynomial. Now what I'm going to do is I'm going to approximate, so P of x. Okay, so P of 2.77. Now why am I using 2.77? It's because I'm trying to approximate the square root of, for some reason, 4.23. And if I do 7 minus 2.77, it gives me 4.23, which is what I'm trying to approximate the square root of. So I have to plug in 2.77 to do that. That's why that value is weird. I don't know. That's like a really weird value. I don't know what we're doing there. But anyway, it worked. So P of 4.23, which is approximately square root of 4.23. Nope, sorry, got that wrong. P of 2.77 is approximately the square root of 4.23, and that gave me 2.057, let's say. All right, now, 3rd degree polynomial, which means we use the 3rd derivative to make it, which means we need the 4th derivative when we're finding the error. So I need derivative f of x, comma x, 4. 4th derivative. Now, is this increasing, decreasing? The numerator is constant, and then the denominator is decreasing. So, no, the denominator is increasing. As x gets bigger, the denominator gets smaller, which means that the overall thing gets bigger. So it's increasing. I think this is increasing. The absolute value of this, right? So I need the absolute value of, let me just write that down. Negative 15 over 16 quantity 7 minus x to the 7 halves. Now, what I should obviously just do is graph this because I'm using a calculator anyway. So the maximum of, oh, I wrote that wrong. Crud. Let me undo a lot of things here. Hold up. And you're not even watching. It's a tragedy over here on the notes that I'm writing. So I'm gonna just skip that. And I'll say I don't know, f1 of x is gonna be the absolute value of this thing. And now I'm gonna graph. So graph, I only need to graph though between, yeah, it's increasing. It's like not a lot, but I only need to look at this thing between 2.77 and 3, which can you even see it? Let me change, wow, this is really gonna be tiny. Let's make the y-min be negative 1 and the y-max be f1 of 3, I guess. What happened there? Is it negative? Why would it be negative? Oh, because negative 1 is so much bigger. Let's do negative 0.001. There we go. Okay, so I had to make the y minimum really, really small because the y maximum is incredibly small. Let me trace this thing. Menu, 5, enter. So it's going to happen at 3. And then I'm going to press enter to paste that and escape. And then control menu, store, and I want to store that as m because that's the value I'm using for m. 0.007. Okay. So, maximum error is m times the absolute value of 2.77 minus 3 to the, that was the 4th derivative we used, so to the 4th, 4 factorial. We're going to store this as set equal to the answer. Really tiny, our 3 decimal thing not going to work for us here. This is actually like nothing's gonna work on this pretty much. Let me go back to the notes and maybe try to straighten these out and see what I can do here. So this, I got overzealous and I wrote this. So I'm gonna move this over and then copy this, put it over here and say it's gonna be of the, so we used the, what do we use? We have a third, so we use the fourth derivative. What was this? Which is, I mean, it's at 3, so I guess we could actually get the exact value and say 15 over 16. So if I plug in 3, I get 4 to the 7. And we're going to use this as m. This is m. M is weird in this case. That's our m value. And then, so then the absolute value of the error, less than or equal to, I'm going to write m because I don't want to handwrite that. Absolute value of 2.77 minus 3 to the 4th over 4 factorial. Did I do this wrong on the calculator? I feel like I used 5. Did I? I did not. Okay, we're good, I guess. And then we store that as e. And then over here, we're going to do p of 2.77 minus e less than or equal to f of 2.77 is less than or equal to p of 2.77 plus e. All right, calculator again. Jeez. Is it so? I don't know. I mean, this is, I feel like I've been doing these for hours at this point, which I haven't, because I'm pretty sure all the videos just straight up don't add up to that. But still, like, 2.77 minus and then p of 2.77 plus You, by the way, can use the var key and should use the var key for these, like var, and you don't have to type every time. These are going to be like so small that, yeah, okay. So the true value is, I mean, we're stuck, right? We need more decimals. Let's see, how many decimals do we need? I'll go 2.0566963. Let's say f of 2.77 less than or equal to, what do you got here? So let me get out of there. I don't even know how many decimals I wrote there. Also, I'm not sure which one I wrote. 2.05 66981. 981. There you go, maybe. All right, true value time. F of 2.77. Yeah, I mean, obviously. So it worked. So I'm going to say that F of 2.77 is approximately, I'm going to go with 2.0567. And it worked. And then let's go back to the notes. It worked. So you can see it. And then we are finally done with the, hopefully by doing these, it gets like so ingrained in your brain that you don't really need to do more of them. I know you're always going to need to go back and kind of like refresh and review. But we just did a bunch and it's pretty straightforward once you get what's going on. So I'm going to cut the video here. I'll see you in the next video where we will be hopefully doing something different. Let me just see. Yeah, all right. Yes. Woo! We're doing something different. So I will see you in the next video.